inspiring the evolution of embedded design since 1988.
Okay, throw it. Yeah, you made it into a cup. Okay, so this is a virtual root beer pong? Yeah. Is that what I hear? Yeah. Okay.
3 Cornell graduates accurately simulate the movement of a human arm to play beer pong using PIC32s and IMUs.
Tell me about it.
Up here in the robotic arm, we have sort of like a 3-degree of freedom servo control arm.
The robotic arm is made of coffee sticks, small servos and a spoon, held together by hot glue and tape.
And so we're using 2 different PIC32s. One is solely for the control of this, and then the other one, we have it here on the sleeve, and it gathers data from 2 IMUs and this pressure sensor over here.
So you have an IMU for the elbow, and you have an IMU for the wrist, and then you have a pressure sensor which you're using as a release.
It's a release mechanism.
So the further you cock your arm back and then press, the further the thing goes. All right, so now
that would be like the furthest, I think.
Neat. All right, so move your arm around now so I can watch the robot move at the same time. And so, over what period of time do you have reliable tracking?
Depends on the motion you make with the elbow. But if you keep a small movement, about 10-20 seconds of enough time to play game, if you move like wide range, then it may get a little less.
But it's still pretty good. It's after all that motion, it looks like it's maybe precessed 30 degrees around the horizontal axis there, and that's pretty good. And you're using a complementary filter on the IMU?
Yeah, so all the calculations are actually done on this PIC32, and all this one is doing getting those the angle data to convert into pulse width for the servo motors.
Right.
And to calculate this angle of elbow and the wrist, we use 98% gyro and 2% accelerometer. So what it does is the 98% gyro is able to quickly capture the motion of the angle, and because there is some integration error, the accelerometer 2% takes account of kind of like bringing it back to the actual angle.
Once you stop it, then it does the static correction.
So another thing that we have going in here is we initially tried to have RF communication between the 2 boards, and although it was working, after maybe like 20-30 seconds, it would become a little unreliable. So in order to have this continuous motion that you can see in here that just keeps going, we just connected them to UART directly. So right now they're talking to each other via UART.
Okay, so in the fullness of time, if you had infinite time, you'd make it wireless because it's almost there.
Yeah, if we had maybe just this one day to debug and then with tomorrow.
So there's also like some delay with the RF packetization and depacketing time. So
you're quite right. In fact, with the XBs, there's quite a lot of packeting time, maybe a quarter of a second.
Yeah, it was actually like 30 milliseconds when I saw it from the Microchip. Yeah,
that's enough that it bothers you.
Yeah, so it slows down the reaction time of the robotic arm, but now it's very it seems pretty real time now.
Oh, I agree. That's very impressive. And it has kind of a oddly realistic look to it too. Yeah, when you pump your arm, it kind of has a. Okay.
It's a prison break.
Yeah. Okay, thanks.
I can also feed someone if I go like.
Your last throw.
Okay, one last throw.
Go back a little more.
Oh,
okay,
miss.
No, another one. Okay. Go back. Okay.
Read more about this project and many more at circuitcellar.com.